Okay, so in the previous video, we derived for laminar flow that the velocity profile in the fully developed section is parabolic. And we also proved that the pressure gradient as flow goes through the tube decreases and is a constant. And so now we're going to just analyze this velocity profile to find the volumetric flow rate, the mean velocity, and the maximum velocity. And so Q equals the integral over the area, over any area, of v dot n hat dA. And here we are integrating in the pipe. And so the area, so our differential area is a ring, because we're assuming the flow is axisymmetric, which it is. Where dA for the differential element, dA equals 2 pi r dr. So this 2 pi r dr, and we're just doing a fictitious plane here. I hat points in the x direction, and v equals u of r I hat. And so for this we use the u of r up here that I derived in the previous video. And if we stuff that in, this equals the integral from 0 to r, 2 pi u of r d r, and we stuff in what u of r is. This equals the integral from 0 to r of minus 2 pi r squared, or cap r squared, over 4 mu dp dx. And again, dp dx, all this stuff here is just a constant, times 1 minus r over cap r squared r dr. And this stuff here is essentially a constant. And recall that this negative sign here basically means that the flow is going in the opposite direction as the pressure gradient. Okay, and we can perform this integral. I'm not going to go through all of the steps, but it's just a straightforward polynomial. We get that Q equals minus pi over 8 times the pipe radius to the fourth, mu dp dx. And note that it's not usually given in this form, but r equals d over 2. And so r to the fourth equals d over 2 to the fourth equals d to the fourth over 16. And so we can basically substitute r to the fourth for d to the fourth over 16. And if we do that, this implies that the volumetric flow rate Q is equal to minus pi d to the fourth over 128, because that's 8 times 16, mu dp dx. Okay, and so that's the volumetric flow rate given a pressure gradient and a viscosity. And note that because of the non-constant velocity profile, where it's parabolic, it's actually proportional to the outer diameter of the tube to the fourth power. So it is so for laminar flow, the pressure drop in the volumetric flow rate is very sensitive to the diameter of the pipe. And so and now for the average velocity. And the reason I'm doing this will become apparent in another video or two. So I'll just call that U average. That is equal to 1 over the area times the integral v dot n hat dA, and that just equals Q over the area. Well, this implies that U average equals Q over the area, and we know Q, and I'll use the R version of it, equals minus pi over 8 r to the 4th over mu dp dx over the area, which is just pi r squared. And so this equals minus, if you substitute in the radius for the diameter, this equals d squared over 32 mu times dp dx. That equals U average. Okay, and so that's what that equals. And again, there are quite a few algebraic steps between here and here, but again, it's just straightforward. It's just straightforward algebra. Or this is equal to minus r squared over 8 mu dp dx. So it depends if you want to work on a radius basis or a diameter basis. Okay, and so that's the average velocity in the tube. And so that means that if you want to compute Q, and you just want to you want to assume a uniform flow in the tube to compute the flow rate, if I integrate the velocity profile over this tube, I get Q. Or if I assume that the velocity profile is perfectly uniform at U average, and I multiply it by the cross-sectional area of the tube, I will get the same volumetric flow rate. Okay, and another piece of information that we will be interested in is the maximum velocity. Okay, and which is at the location du, dr is equal to 0. And so du, dr, we actually already found that while we were integrating the ODEs, or you can just take the time, or you can take the r derivative of our function here and just start going through it. It's rather straightforward. So that equals 2r or half r over mu dp dx, and the max velocity occurs where the slope is, of course, 0, and this is equal to 0 at r equals 0. Okay, because dp dx is non-zero. So Umax equals u at the center line, or u at a small r is equal to 0. Because remember, this is a tube, and we're measuring r from the center line of the of the tube right here, and so that equals minus r squared over 4 mu dp dx times 1 minus r over cap r squared, and small r is equal to 0, so this term goes bye-bye, and that equals minus r squared over 4 mu dp dx. And now something that is pretty interesting here is the ratio of Umax to U average. Then Umax over U average equals minus r squared over 4 mu dp dx divided by U average, which is minus r squared over 8 mu dp dx. And that implies that Umax over U average equals 2. Okay, and so that means that the value of the velocity at the center line here, Umax, is exactly twice the average velocity. Okay, and I also showed that for a parabolic profile far earlier in the class. Okay. And then also using Umax, we can simplify the velocity profile to get rid of that nasty little constant in front of it. U equals minus r squared over 4 mu dp dx times 1 minus small r over cap r squared. Well, this whole thing is just Umax. So this equals Umax times 1 minus r over cap r squared. Or you could say that Umax equals twice the average velocity. Okay, and so you will quite often see the velocity profile written in terms of Umax. Okay. So why do we care about this velocity profile? Sure, we can find the average velocity in Q and the maximum velocity, all that fun stuff, but why do we care? Well, let's look at the shear stress. Okay, so if I consider a free body diagram over a large section of the tube. So here's the tube. And I'm considering a free body diagram that looks like this, and the entire T of the control volume is in the tube, and the length here is L, and this here is P at X. This here is at P at we'll just call this P2. And we have pressure here, P1, but also at the wall we have shear stress. Okay, and so we did a big long control volume here, and we know that because it's fully developed, tau wall is equal to a constant, right? Because it's fully developed, the value of tau wall on this portion of the wall of the tube is the same as it is over here, is the same as it is over here, is the same as it is down here, and is the same as it is down here. Okay, and so now I'm just going to do a free body diagram, so we know that the sum of the forces is equal to 0. This means that P1 times the area, or pi d squared over 4, minus, oops, wrong one, minus the P2 times pi d squared over 4, minus the shear stress, which opposes the flow. So here I'm assuming that there's a flow going from left to right, and so there's a shear stress that is opposing that flow, and so that would be some tau wall times the surface area of this piece here. And so that would be L times 2 pi r. Or I should actually write that as pi d. Okay, where r is the outer radius of the tube. And that's equal to 0. So in the free body diagram, I have summed the forces. And so here, I can just cancel out a pi d and cancel out a pi d. And so this implies that P1 minus P2 equals 4 times L tau wall over d. Okay. And I will define this as our pressure drop delta P. So this implies that delta P equals 4 L over D times tau wall. And so that is really what we were after here, is this pressure drop. Because we're going to be analyzing piping systems, and we might have a very long pipe, and we want to figure out how much pressure drop is going to occur, which is going to dictate the size of the pump and things like that we are going to need to do. Okay, and so now that we know the velocity profile in tau is equal to mu du dr. And so tau wall equals mu du dr at the outer radius of the tube. So all we need to do is use our velocity profile and take the derivative of it and evaluate that derivative at the upper wall of the tube. And so that's why we went through this whole big analysis to find the velocity profile. Okay? And so evaluate. I don't know why this thing does it every now and again. Evaluate tau wall that equals mu du dr at r equals cap r. And we substitute in our formula Umax times 1 minus r squared over cap r squared. And we just take the derivative of that. That equals mu times minus 2r over cap r squared evaluated at r equals cap r. Oh, and I forgot to multiply that by Umax. And that implies that the wall shear stress, substituting that in, equals minus 2 mu over cap r times Umax. Okay, or this equals minus 2 mu over r times 2 U average, using the result that Umax is equal to twice of the average velocity. And then I'm going to convert this r to d. R equals d over 2. So putting everything together, this implies that tau wall equals minus 8 mu over d times the average velocity in the channel, or in the pipe, I should say. So then, now that we know this result, we can stick that into the delta P relation, And we had that delta P is equal to 4 L over D times tau wall. So that equals 4 L over D times minus 8 mu D times the average velocity, or delta P equals minus 32 L over D times mu times the average velocity in the channel, or the tube I should say, over D. Okay, and I'm writing this in kind of a funny way because we're going to simplify this in a bit later on. Okay, and so if we know the average velocity in the tube and the average velocity equals Q over A, and so if we know the volumetric flow rate, the size of the tube, and the length, and if we know that the flow is laminar, we can compute the pressure drop. And then I'll describe how to determine whether a flow is laminar or if it's not laminar in a few minutes. And so now the pressure drop relations usually aren't given in just a delta P, nice little delta P formula like this, because for turbulent flow it's much more complicated. But for the pressure drop, it is customary to non-dimensionalize delta P by the dynamic pressure, which is 1/2 rho U average squared. Okay, and you can you can come up with the scaling using a Buckingham Pi analysis. So we get delta P over 1/2 rho U averaged squared is equal to our relation here, and I'm going to drop the negative sign because it is understood that the pressure drop decreases. So times 32 L over D times mu U average over D divided by the dynamic pressure 1/2 rho U averaged squared. And you can get this non-dimensional parameter here using Buckingham Pi sans this 1/2. Because remember I said when I did Buckingham Pi is that it's customary in some applications to multiply the non-dimensional parameters by factors of 2 or 1/2 and things like that. And this is one of those cases. Because if you multiply, because this parameter down here is the dynamic pressure by definition. Okay? And so I simplify this, and I get 64 times L over D times mu over rho D U averaged. Okay, and this parameter here is 1 over the Reynolds number of the channel, or of the tube I should say. So delta P over 1/2 rho U averaged squared is equal to L over D times 64 over RE D. Okay? And so if you were to do Buckingham Pi, you would find that delta P over 1/2 rho U averaged squared is equal to some function phi, I'm not going to use f, of RED and L over D. And so if you used Buckingham Pi to analyze the non-dimensional parameters of what govern pressure drop in a tube, for a laminar flow, this is exactly what you come up with. And by solving that exactly, we actually come up with that delta P over that parameter is equal to a function of L over D and the Reynolds number. And so that's actually born out of the analysis. And now delta P then is equal to 64 over RED times L over D times rho U averaged squared over 2. And I'm going to set this equal to something here, and this is going to suggest a form, this general form here for the pressure drop. We are actually going to use it for turbulent flow too, except for this constant here. We are going to generalize that and call this sum F times L over D times rho U averaged squared over 2. And this F is called the Darcy friction factor. And for laminar flow, F equals 64 over RED. Okay? And so, and this form also, we will also use this form for turbulent flow in the pipe. It's just you have a different Darcy friction factor. Okay? And also, delta P is sometimes written as, and we will use this for the minor losses, equals KL times rho U averaged squared over 2. And this is used in scenarios where L over D doesn't make sense. Okay, and we will use that when we analyze the pressure drop in an elbow or a valve or something like that. Okay, so delta P equals F L over D times rho U averaged squared over 2, and that equals some loss coefficient KL, rho U averaged squared over 2. Okay, and this KL is a loss coefficient. Okay, and RED, I'm going to just remind you of what RED is for laminar flow. Again, I can't stress enough here that this formula is for laminar flow only, and RED is equal to is the Reynolds number, that's rho U averaged, times the diameter of the pipe over mu. Okay? And so that is how we analyze, and so these forms here actually motivate the pressure drop. And essentially how you find pressure drop in a turbulent flow, and I'm going to discuss that more in the next lecture, is you still analyze it using these formulas right here, except for the Darcy friction factor is a different function. And so for laminar flow, if you have it, a laminar flow, it's just equal to 64 over RED. And now how to determine if a flow is laminar. If a flow is laminar, RED is less than 2300. Okay, and so that's a good practical criterion for a laminar flow, is that the Reynolds number of the flow in the pipe is less than 2300. So if you compute the Reynolds number and it's less than 2300, you can use this formula for the Darcy friction factor. If it's greater than 2300, then you got to go through the turbulence stuff that I'm going to discuss in the next video.